Hi everyone, I'm Fiona, and I'll be presenting our paper, Gait-Synced Translation Gain for Naturalistic VR Motion, joint work with Senzai Xu, Kui Huang, Ariel Shamir, and Songhai Zhang. One of the fundamental challenges in immersive virtual reality is the mismatch between the scale of virtual environments and the limited size of physical tracking spaces. Users may walk through expansive virtual cities, yet physically remain confined to a small room. Redirected walking addresses this mismatch by applying subtle motion gains that manipulate users' visual proprioceptive sensations while steering them away from real-world boundaries by remapping virtual and physical environments. Among RDW techniques, translation gain is perhaps the most direct. It scales the mapping between physical and virtual displacement. However, translation gain has well-established perceptual limits. If the manipulation is too large, users begin to detect inconsistencies between visual, vestibular, and proprioceptive cues. This can reduce presence and, in some cases, lead to sickness. Hence, translation gains are typically constrained to a narrow range, approximately 0.86 to 1.26. This narrow window limits how much virtual distance can be mapped onto a given physical trajectory. Importantly, current RDW systems apply translation gain continuously and uniformly, updated frame by frame, regardless of the user's locomotor state. In other words, the system is designed around the most perceptually sensitive moments of walking. However, human sensitivity to visual vestibular discrepancies is not constant. It fluctuates over the gait cycle. Biomechanics and perception research show that during double limb support, when both feet are on the ground and posture is stable, sensitivity to motion discrepancies is relatively high. In contrast, during single limb support, the body is in a state of controlled imbalance. The center of mass shifts, vertical head motion increases, and the sensoromotor system is already processing greater perturbations. During these moments, sensitivity to fine visual vestibular discrepancies decrease. This observation led to our central hypothesis. If perceptual sensitivity fluctuates across the gait cycle, then translation gain should not be applied uniformly. Instead, it should be redistributed temporally, concentrating stronger manipulations during phases of reduced sensitivity. We call this approach Gait-Synced Translation Gain, or GSTG. GSTG dynamically modulates translation gain in synchrony with the user's gait. When the system detects the onset of single limb support, it briefly increases the gain. As the user transitions back to double limb support, the gain smoothly decays toward baseline. Rather than increasing gain magnitude globally, we strategically shift when gain is applied. By aligning additional virtual displacement with natural biomechanical perturbations, the manipulation is perceptually masked. The visual motion is interpreted as a natural consequence of walking rather than an external distortion. This allows us to achieve higher effective translation gains without exceeding perceptual thresholds during sensitive phases. To ensure practical deployment in real-world VR systems, GSTG cannot depend on additional hardware, such as ankle trackers or instrumented footwear. Therefore, our implementation relies solely on sensors already available in standard head-mounted displays. During walking, the head follows a rhythmic vertical trajectory. To estimate gait phase, we extract vertical head acceleration from the HMD's inertial measurements, apply smoothing to reduce noise, and detect characteristic transitions corresponding to gait phase changes. Once gait phase is identified, translation gain is modulated dynamically. The target gain scales with forward walking velocity, allowing larger modulation at higher speeds, where biomechanical perturbations are naturally greater. To prevent perceptible discontinuities, we apply asymmetric temporal smoothing, enabling rapid gain amplification during single limb support and gradual decay during double limb support. This design ensures low latency synchronization while maintaining perceptual continuity. Before evaluating perceptual effect, we needed to ensure that the HMD inertial data reproduces established biomechanical patterns of human gait. Validation against high-precision ankle trackers confirmed that HMD-based acceleration reliably predicts gait phase with sub-perceptual delay, demonstrating that hardware-agnostic synchronization is feasible. With the system validated, we conducted a measurement study to estimate perceptual detection thresholds. 20 participants completed a 2-alternative forced choice task across 5 different virtual environments. In each trial, participants walked a fixed physical distance and judged whether the virtual distance appeared larger or smaller than the physical distance. We compared previous continuous translation gain with GSTG across a range of magnitudes and fitted psychometric curves to estimate upper detection thresholds. Gains were sampled densely across the perceptual range and repeated multiple times per condition. For continuous translation gain, the upper threshold was 1.233. For GSTG, the upper threshold was at a base gain of 1.008. When accounting for the temporally concentrated gain spikes, this corresponds to an effective average gain of approximately 1.436 under continuous translation. In practical terms, GSTG enables more than a 15% increase in imperceptible gain compared to the standard continuous method, effectively expanding the usable translation gain window beyond the previous 1.26 constraint. Importantly, this effect was consistent across all 5 virtual environments, suggesting that the masking mechanism is primarily biomechanical rather than scene-dependent. We then evaluated subjective experience. In a second study, another 20 participants compared GSTG and continuous translation gain at 1.0 using ratings of locomotion naturalness, presence, speed perception, and physical effort. In each trial, participants walked a fixed physical distance and answered the questions according to their experience. GSTG achieved significantly higher ratings for speed naturalness and perceived effort. Despite enabling faster traversal of the virtual environment, it did not reduce perceived naturalness or presence. There were also no significant differences in step matching, indicating that gain modulation did not introduce noticeable gait inconsistencies. To assess user comfort, we conducted an extended exposure experiment and administered the simulator sickness questionnaire before and after the session. Another 20 participants experienced both GSTG and continuous translation gain over 32-minute sessions where they would undergo various tasks across 4 different virtual environments. No statistically significant differences in sickness were observed between the 2 configurations. There are several directions for future work. Our detection threshold measurements were conducted during straightforward walking without controlling for speed. Since walking speed negatively correlates with gain detection thresholds, future studies should standardize speed to improve measurement precision. Although our gait detection approach was validated against biomechanical ground truth, further evaluation with a larger sample size across more diverse walking styles and complex head movement patterns would strengthen generalizability. Finally, GSTG was evaluated in isolation. Integrating gait synchronized modulation with other redirected walking techniques, such as curvature or rotation gains, may further increase efficiency and naturalness. In conclusion, our work demonstrates that in redirected walking, timing is just as important as magnitude. By treating the human gait cycle as a design resource, we can leverage natural moments of reduced perceptual sensitivity to hide substantial spatial manipulations. In terms of spatial efficiency, GSTG enables users to traverse approximately 15% more virtual distance than its respective continuous method. Importantly, it remains perceptually imperceptible, maintains user comfort, and requires only a standard HMD. Looking ahead, aligning VR redirection strategies with the body's intrinsic rhythms opens a promising path toward more seamless and scalable virtual locomotion. Thank you.